All right, so today we're going to review periodic trends. We're going to talk about some organic chem, get you ready for things you'll see in the future. Let's review some periodic trends. If you don't have a periodic table handy, I'll give you one of my little ones here so that you can just jot things down on your periodic table. So you can just kind of keep a running tally of our periodic trends we're learning today. So draw a generic periodic table in your notes. That works too. Okay. So let's talk about periodic trends. Now some of these we've already talked about, some of them we haven't, so that's why I call it a review. All right, let's talk about radius, the size of the atom. The radius increases down a group. Increases down a group. Now whatever you learn going this way, it's always the opposite going the other way. So if it increases down a group, so atomic radius increases going down, what's it going to do going across? It's going to be the opposite, right? It decreases across a period. Atomic radius decreases. Right? So you don't need to memorize, picometer lengths here. You can just look at your periodic trend. If I said, okay, who's bigger, sodium or argon, right? You don't need to know that one of them's got a radius of 186 picometers and one of them's got 98. You don't need to memorize that. Just know your periodic trend, that going across a period, right, the radius decreases. If I said who's bigger, sodium or cesium, right, sodium and cesium are in the same group, you just know your periodic trend, 265, I don't need you to memorize the number, right? You just need to learn the periodic trend. So if you know it one way, it's the opposite going the other way, which is convenient. That's nice and convenient. All right, now what causes this is something called effective nuclear charge. And we can actually do some pretty gnarly calculations on this, which we're not, just throwing that out there. But let's at least understand where this trend comes from. Okay, so our electrons are attracted to the nucleus, right? Because they're protons hanging out in the nucleus. And they're also repelled by other electrons, right? Electrons are going to repel each other, but they're going to be attracted to the nucleus. And so the nuclear charge that any electron experiences is going to be the effect of both of those factors, right? Does this make sense? Electrons will repel each other, but they're going to be attracted to the nucleus. And so here's some pictures. This isn't from your current textbook, I don't think. I can't remember which book this is from. But let's just look at helium. Two options here. Okay. So here, there's just one electron around, right? It's just feeling an attraction to the nucleus. It's not feeling any repulsions. Whereas here, there are two electrons around, right? Because those two are repelling each other, this one's easier, or this one's easier to remove. Does this make sense when you start throwing that extra electron? Those two repel each other, so this one's going to be easier to remove, whereas this one, if there's not another one in its vicinity, it's harder to remove, so there's no repulsion. See what I'm saying? If we're looking at another one, again, one by itself versus in close proximity to each other, this one will be easier to remove than this one, again, because we've got those repulsions going on, whereas we're not having those repulsions there. And so here's some pictures to represent that. So in other words, here are the radii, right? Here's the radii if you're going across the period, right? There's the radius getting smaller, right? But the effective nuclear charge is getting bigger going across. So again, another way to think about it is you've got a more positive nucleus versus a more negative electron field, okay? And again, that's about as far as we're going to get into effective nuclear charge. You can do some calculations on it, but I'm not going to make you do it. So using your periodic table, which of the following would have the largest radius? I mean, there's no math to do here. Just look at your periodic table and figure it out. Which one's going to be biggest? Chlorine, sodium, silicon, or sulfur? Which one's biggest? First, you need to decide if they're in the same group or the same period, and then apply your trend. Who's the largest? All right, sodium's biggest. Going across, right? Across the period, radius decreases. Effective nuclear charge increases. Okay, what about these? Who's going to be the smallest? Apply your periodic trend here. Who's the smallest? What is the periodic trend? Let's first establish that. Going down a group, what happens to radius? It increases. So who's going to be the biggest? Right, lead's going to be the biggest. Right, increasing down a period. I mean, down a group. Now let's talk about ions. Okay, ions are different. Think about why. Cations are smaller than their parent atoms. Think about why. Think about why. You've lost an electron. Just think of it in terms of, human words. If you lose weight, most people, you're smaller, right? If you lose something, it gets smaller. Think about why. If you lose that electron, so when sodium loses an electron, becomes sodium ion, the electron cloud shrinks. It gets smaller. Right? Removing the electron pulls the atom closer together. So if you want to think about it in terms of you've got one fewer electron out there in the cloud that you're dealing with, right? So those repulsions are minimized and they can get all closer together. Does this make sense that a cation would be smaller than its parent? If you lose 50 pounds, most people are smaller than when they had 50 pounds. What do you think will happen with an anion? A monatomic ion that's an anion. It becomes bigger, right? Monatomic ions, when they're an anion, become larger, right? You've got more electrons in there now. Adding an electron or two or three, right? You're increasing the repulsions in the cloud. You're making that cloud get bigger. So an anion is bigger than its parent, and a cation is smaller than its parent. I mean, this is just kind of, I don't know, makes intuitive sense to me, right? Adding versus taking away. If you gain 50 pounds, probably look a little bigger than when you lost 50 pounds. I'm gaining some weight here. I think I look bigger. So maybe it's all in my head, but I don't think so. I think I look bigger too. Right? So we can now apply both periodic trend and we can think about ion as well. Now we've used this word already when we were doing electron configurations. We used this word when we talked about atoms that have the same number of electrons, right? Isoelectronic means they have the same number of electrons, right? Isoelectronic means you've got the same number of electrons. So a group of ions with the same number of electrons, we say are isoelectronic. So just like when we were talking about electron configurations, right? We talked about isoelectronic then as well. Iso meaning same, so same number of electrons. So if we do this one together, right? Na plus, how many electrons is that going to have? 10. Mg2 plus, how many electrons is that going to have? 10. Aluminum ion, 10, 10, 10, 10, right? All of those have the same number of electrons. They're isoelectronic. Right, so this is what we just said. Anions are larger than their parents, and cations are smaller than their parents. So of this group of ions, which ion is the biggest? They're all +1 cations. So which one is going to be the biggest +1 cation? What's the answer? It's easy, right? which is the largest of this group? This one's a little bit tougher. We can immediately rule out which ones as not being the biggest. The two cations we can rule out, right? Because they're going to be smaller than their parents. So now we're just deciding between the two anions, which one's going to be the biggest. Well, iodide ions down here, whereas bromide is down here, right? Iodide's the biggest, 206. Do we see how we came to this conclusion? All right, let's talk about ionization energy. So this is another periodic trend we can predict from the periodic table. Okay, there are nasty calculations that can be done to calculate ionization energy, which we're not going to do. We're just talking about it from a periodic trends perspective. Okay, so the energy required to remove an electron from the ground state, that's what we're talking about when we say ionization energy. All right, so first ionization, second ionization, third ionization, fourth ionization, etc. Right, so removing the first electron, then removing another one, then another one, then another one, another one, okay? Does everyone see why we've got these little numbers after it? First ionization, removing the first electron, second, third, fourth, fifth, sixth, seventh, eighth. Obviously, when you start getting to the eighth ionization energy, that's an extremely large number. Why? Because you're into the core electrons then. And I'll show you some data to represent that. Now let's talk about what the trend is. It's requiring more energy to remove each electron. Right, so look, let's think about the electron configuration for sodium. Right, sodium's electron configuration is Na would be, what was in parentheses? Ne, and then what? 3s1, right? It's got one valence electron. So the energy required to remove that first valence electron is 495. Remember, these are all core. These are core, whereas these are valence. Right? So that first ionization energy is getting rid of that valence electron. Look what happens when we get to the second ionization energy. If you're trying to make Na plus 2, look how much energy that takes. Woo, that's a lot. Why? Well, because the first was getting rid of a valence electrons. This is getting rid of a core, right? A core electron is a lot harder to remove than a valence electron. Same thing happens with Mg, right? If we're doing magnesium, I don't know if I'm in the frame or not when I write right here, but oh well, we're going to do it anyway. Ne3s2, right? There are 2 valence electrons. So, I mean, those aren't small numbers, but they're small compared to the third ionization energy, right? Because you're removing the first 2 valence electrons. Okay, that's a decent number, but it's nothing compared to 7,000 to remove core electrons, right? Once you move for valence electrons, getting those core electrons costs a ton of energy. Okay, so you can see this trend. Every time you remove an electron, especially once you've removed the valence electrons and you're getting into core, the numbers are just astronomical, right? So that's why the leap happens after you removed all those valence electrons. You're getting into core. So here's the trend. It increases across a period. So you can add this to your periodic table. Ionization increases across a period, and ionization energy decreases down a group. So it's the opposite of our transit radius. Everybody good on the trend on ionization energy? So there it is again, removing electrons, just a different graphical representation. All right, we've already talked about electronegativity. You guys know this trend. What is the trend in electronegativity? As you're going across, what happens to electronegativity? It what? Increases, right. We talked about this one way long time ago when we were doing Lewis structures. Increases across a period and decreases down a group. Right? Fluorine's most electronegative elements. We say electronegativity is a measure of how well you share electrons in covalent bonds. Right? So we already know this trend. We talked about it a long time ago. Most electronegative element, right? We're increasing across a period and decreasing down a group. So we've learned this one already. All right, so those are our trends that we're reviewing today. Radius and ionization energy are the ones that we hadn't officially talked about yet, but we've already talked about electronegativity. If you know it for growing across, then just reverse it for down a group. So that's the convenient part. If you just learn it one way, right, then you know the other way by default, by reversing. Questions from me on periodic trends? All right, so I know that's a big jump to go from periodic trends to organic, but that's okay. Let's do one more just for good measure. Rank these in decreasing size. So on your paper, take a second and rank these in decreasing size. I'll pause it for a second. All right, so we are decreasing size, which means we put the biggest one first or last. By decreasing size, biggest one goes first, right? Do we agree? All right, one more for you to try. Rank these in increasing size. And I'll pause it for you again. All right, so we've got this last one to do. Do we agree? Increasing size means smallest one goes first. Do we agree? All right, we'll just skip